So here we would have an original image. I will not touch it because it takes quite some time to update the image, so it is not so useful. So the thing is, this is about the phobia. I can see it. Let me see if I can make it bigger. We decided that we cannot, no? A little bit. So, yeah, so here we have placed the phobia in this location. And then we have applied this logarithmic transformation that I showed you in the slides. And you see that where the center is, we have a lot of details, but as you go farther away from the center, you start losing all the details. So this is the effect of the phobia. And the thing, we have something, I think in English it must be the same, saccadic movement. So the eye is moving all the time. So it is called saccadic movement. And it is looking at different places, and then it is the brain who is integrating all these small details over time, so that we have the impression of having a fixed image. Okay, so let's close this one. Then we can explore some other ideas. So, for instance, this decrease saturation. So we already know what saturation is in this HSV space, so we can increase the saturation, so we are closer. Doesn't seem to be working properly. So we should be closer to very saturated colors. And here at 0, yeah. So 0 is the, yeah, it is working. So 0 is the gray image, and then we are going farther away in the direction of the colors, or in the opposite direction of the colors. You see? So now we are in this HSV space, and either you move in the direction of each one of the points, or you move away from it. So that is what this slider is doing. Then what else do we have? Yeah, this is not working so well. Let's look at this one. So, for instance, you may remember this idea of pixelization. So we can take an image and then pixelize by a factor of 2 each one of the bytes. Let's see how it looks like. So barely visible any effects, but we have divided by 4 each one of the channels. So we have 4 times less numbers in each one of the channels. Now 16 times less numbers. Now we start to see, and 8 times, and now it is clearly visible. So now let's explore if this also applies when we do it channel by channel. So for instance, let's say we have we separate the 3 bands, and then we apply the 8 factor reduction in the red and the blue channel, but not in the green channel. Let's see how it looks like. So these are each one of the channels separated, and you see it is not as bad as this one. Right, the red channel, we can see the small, the big pixels. Right? Otherwise, the general appearance, it is much better than this one. So it is, again, this idea that we are much more sensitive to the green channel, to anything else. Let us try just for fun. No, just for fun. Decrease this one. Yeah, let me go for 4 in this 2. So probably we will not see much of a difference. So the original was close to this one. So we can compare these two. So they look very much alike. Okay, we see a little bit of pixelization in the red. It is by a factor 4. Okay, so what else can we do? So all these are the ones. We still have an image here. Okay, so now what else can we do? All these are optical illusions. So for instance, we can see this one. So all these blue lines, they are parallel to each other. But it is difficult to see that they are parallel because of the location of the black and white bands. It is difficult to say that they are parallel, but they are parallel. So this is again one demonstration that what we see are the borders, and then our brain is interpolating all the information around, making use of a priori knowledge of how the world is constructed. So for us, all these black and white areas, they are kind of shades. And this is a shading pattern that it is quite unnatural. So that is why our visual system is confused. Okay. Then, yeah, this one we have already discussed. This is the one with this box that is. See? Yeah, it is shown here. Okay, so it is this box that has the same gray value here and there, but because of the shades, we think that this side is darker than the other one. But if we close, for instance, you see, they have the same color. So it is only because of the edge that you think that they have different colors. But if you remove the edge, then you see that they have the same color. Okay, what about this one? This one is this one with where we had these branches of the spiral. So we see kind of green and cyan branches or arms of this spiral, but actually they both are green. Only that because of the surrounding, so this surrounding is made in such a way where the inhibition of the lateral inhibition of neurons, it makes us think that these patterns are, this arms is green and cyan, but yeah, no, both are green. You see that here? Both are green. And again, all these optical illusions, they have to play with kind of unnatural images, because otherwise, for natural images, when you look at anything that is in the real world, you have these optical illusions so often. Our brain and our visual system is very well adapted to natural world, but not to this kind of pattern. Okay, so what else do we have? Okay, so let me load the image again. This one. Then, color correction. So this one, you can see this is the color cube that we were discussing the other day. So this would be the 0, 0, 0 corner, and this on the other side would be the 1, 1 or 255, 255, 255. So this would be white, this would be black, and then you have the red axis. So all these points here, they are red. All these points here in this axis, they are blue. And all these points, they are green, pure green, with different intensities, but they are pure green, pure red, pure blue. And then you have all kind of, don't you get that? pensándolo?
Que son muy largos los chistes. Va una canica y vuelta.
Right. Okay, so these are these sides that these faces of the dice that we were discussing the other day. You see, this is made purely. This is the red, blue plane, and then in this corner here we have magenta. That is the addition of the two. But then we have all kind of degradation between the two. The same here. This is the green, blue plane. And then here we have cyan, and then all the kind of degradation in between. And we cannot see cats. The person who did this tried, and then for triangles, she did more or less correctly. But at some point, we should have hexagons and these hexagons are not calculated. So, yeah, but you can imagine that these are kind of cuts through this cube, only that they have not been properly calculated. Okay, so what else? We have HSV conversion. For that I need an image. So let's open our favorite image, and then we convert it to HSV. So now we have the two decompositions. So it is red, green, blue. That is the ones that we are used to. But this is the HSV conversion. So you see that the value is kind of an overall summary of the whole image. It is kind of how much intensity do we have, how many photons do we have, disregarding of what is the wavelength of those photons. And then the saturation you already know, that is how far you are from a gray value. So here you are not far from a gray value, so you should have zeros. And then here that you have some colors, then you should be farther. So all these white areas, they're zeros. And the rest, because you have colors, you are away from zero. And the hue is the angle between the red and your color. So these areas that are in the cell cytoplasm, so these areas that are red, they should have a small angle. And these areas that are blue or green, they should have a higher angle, and that's the case. And then this image is interesting. It is like, what is then now? If you put these planes in the red, green, blue bands, and you represent it as a red, green, blue, what do you see? So you see this is the red, this is green, and that is why most of the image looks like green, and then blue. But it is just a matter of representation. So it is not that that this image is this one. It is only that if you now play with these planes and you put them as RGB, it looks like the deformation is the same. You have not lost any single bit of information. What else do we have? Okay, so let's close this. Yeah, and yeah, the color corrections we will see today. Actually, it is a little bit inconvenient to use here. Okay, any question? Do you want me to play in some particular way here? No. Okay. So let us stop sharing. So stop sharing, and we will start sharing here. So share the whole screen. And here Okay, so now let us think of the following. So let's say that if we have a degraded image, a color degraded image, and we want to transform this color degraded image into something that looks better. You may remember these two cameras pointing to some boxes, and the boxes look differently. Okay, so we saw a technique to do that. That was this histogram matching, but we may use another technique. Okay, so this is just a representation of that, in which, okay, so let's say that you have some red, green, blue values at a particular location, and then you want to look for a transformation that transforms those RGB values into something different. That will be the RGB, but now of the image J. And here you have some examples. So let's say that you have this original image, and you want to make it more blue, more magenta, more red, or whatever. This would be actually not so useful because you would be degrading your image. But maybe what you have is the opposite. So you have, I think, something less than good. Yeah, this is what we really want to solve. So let's say that you have a degraded image. You don't have the original. In this case, because it is a simulation, we have the original. But let's say that all you have access to is the degraded image. And you know that those colors are unnatural. And you want to make them more natural, like these ones. Okay, so how to do that? Okay, so you need to find some transformation that transforms colors from one space to the other. So from the original image I to the final image J. And this is done through functions. So this is a nonlinear function. This would be a linear function. Okay, so let's look at this a bit more. Okay, so let's say we have image I, we have image J, and we have a transformation between those. And that transformation can be linear or non-linear. So, and we already know what linearity is. So, transformation phi is linear if it fulfills the following two properties. So, the first one is that if you take a couple vectors R1 and R2, and you apply the transformation to it, what you have is the other one is that if you take a vector and you scale it, then the output should be this. So we had a couple of propositions there. So one of them was this one. Okay, so one of them was this. So first one was non-linear. So the first one was, okay, so 255 times R divided by 255, and then gamma, 1 over gamma. And then 255, the green channel divided by 255, 1 over gamma, and then 255, blue channel divided by 255, and then 1 over gamma. So if you try to do that, so how do I know that this is non-linear? If I try a couple of colors, let's do it with the first one. So if I try a couple of colors, then I will have 255 divided by 255, 1 over gamma. And in general, this is different. This is different from what I should have. So what I should have is 255, and then R1 divided by 255 plus 255, R2 So those two things are different. So this is a non-linear transformation. Okay, the other proposition was the following. Okay, so let's say that you construct your image J, and I is a vector, so I is the RGB components. So you multiply that by I, that is a vector. So this is a matrix, a 3 times 3 matrix. This is a 3 times 1 vector. That will give you 3 times 1 vector. So now, let's see if that is linear. Okay, so if it is linear, we should have the two properties. So let's say that I have an image that will be the addition of two images, and then by the properties of the multiplications of vectors and matrices, this is I1 plus I2. And those two are vectors, and this is exactly J1 plus J2. So it fulfills the first condition. What about the second? So now I multiply this by A, and then again by the properties of multiplication, this A can go out. So it is this thing, and this is AJ. 1. Okay. So if you add two vectors, what you have is the addition of the two outputs, and if you multiply an input by A, what you have is the multiplication of the output also by A. Okay, so this transformation is non-linear, this transformation is linear. But in general, both are transformations, so both follow this pattern. So you take an input image, you apply some transformation that is well defined, and then you have an output. Okay, so now, for instance, let's think of these transformations. This transformation keeps G and B the same, and then the red channel is multiplied by a scalar factor. Okay, so we are multiplying these by some number. So for instance, we go from 125 to 175. So the scaling is 175 divided by 125. And what we are doing is, in the RGB space, you are taking this vector that was the original. Where is it? So you are taking this vector that was the original color. Yeah. Sorry. And then the red channel you are multiplying by something. So you are moving from this point to this point. But the green and blue, they remain the same. You see, the green doesn't move, the blue doesn't move, and only the red is shifting up by this scaling from my matrix. This is just in colors, so how it moves. So the red channel becomes more red. And then you can do the same in the green channel, and then you can do the same in the blue channel. So just again, so red and green would stay the same, so red stays the same, green stays the same. So we are going from this point to this other point. But this extra multiplication, what we are gaining by this scaling in the blue channel. Okay, so these are scaling matrices, and you can have the scaling of the three. Okay, so you can scale the three channels at the same time in a single matrix. And in general, any transformation of this shape will have this form. So you will have arbitrary numbers here, and then we have to look for the numbers that apply the transformation that we are interested in. Okay, so let us go. I think it is more understandable if we put the problem first and then we try to solve it. Okay, so let's say that you look at this plane and then you say, okay, this color here, that is a kind of green, should be more this blue. So for doing that, what I will do is to take one color here and say, okay, this is the color I have, this is the color I want. And the color I want is almost the same. So you see this 1770, 122, 121, but the blue channel is now much stronger. So this is a boost of this blue channel, but we already know how to do that with the scaling matrix. And then what about this one? Again, red and green behave more or less the same, but now the blue channel is shifted up. Maybe not that much as before. So now the scaling is much smaller. You can see that the boost here is much bigger than the boost there. Okay, but I want to transform this color into this one. Then you look for another point and you define again your transformation. Okay, this color should be this one. And again, now the transformation is stronger again. You see, it is almost an increase of by 60%. Then you look for another color and you do the same. So this point, this color here should be transformed to this color. So at the end, what you have is you have to look for a matrix such that when you apply this matrix to this point, you get this one. When you apply this matrix to this point, you get this one. Okay, so let's think of. Okay, so let's move to here and say, okay, so let's say in general, I will have a color Ri, Gi, and Y. I have to multiply by a matrix. So this is A11, A12, A13, A21, A22, A23, A31, A32, A33. And this has to be equal to Rj, green J, blue J. Okay, so in general, so this is an equation of this form. So you have a color J, you have a matrix, and then you have this color I. In general, when we write equation systems in this way, which is our unknown. In algebra, your unknown used to be this one, right? Ri was used to be the unknown, but now the unknown is not R. Ri we know. What we don't know is the matrix. So our unknown now is the A. Okay, so let's look. Let's solve for the A. So I can reorganize this in a different way. So let us multiply this. So now I can put my matrix here. That is what I want to solve. So this is my unknown vector, and I have a big matrix. Okay, so let us write the same addition that we have here. So here I have some multiplication of this vector times this vector. So let me write it in that matrix. So A11 is multiplied by I. A12 is multiplied by AI. And then A13 is multiplied by BI. And then I have a lot of zeros. Because all these numbers here, they're not multiplied by anyone in this line. You see? Okay, what about the second? So the second one is multiplied A21, A22, A23. So it will be 0, 0, 0. Then RI, GI, BI, and then 0, 0, 0. But what about the last one? The last one will be 6 zeros, so a lot of zeros, and then RI, GI, BI at the end. Okay, so now I have rewritten my equation system in a way that I'm more used to. So now my unknowns are a column vector on the right. Okay, how many, if I give you a pair of coins, so I give you this color should be transformed into this color. How many equations I'm giving you? 3 equations. We have 1, 2, and 3. So you know that this times this should be equal to this number, and then this times this should be equal to this number. The third row by the column should be equal to this number. So you have 3 equations. How many unknowns do we have? We have 9 unknowns. So we have 9 unknowns and 3 equations. So with just one pair, I'm giving you 3 equations. And it makes sense because I'm telling you this RGB should turn into this RGB. So I'm telling you 3 constraints. Okay, so if I want to solve for these 9 unknowns, how many pairs do we need? 3. So we need 3 pairs of this form. So we need that R, let me do it first in that. I will write it 3 times, then put numbers. Then let's put the numbers. 1 into 1, 2 into 2, 3 into 3. So I have to give you 3 pairs. These vectors should be transformed into this. These vectors should be transformed into this. And these vectors should be transformed into that. And then, now with these 3 pairs, you would be able to solve for a unique A. Okay, good. What if I give you 4 values? It is not that easy. Okay, I give you 4 values. Sorry. In our slide, we have 4 pairs. 1, 2, 3, 4 pairs. So now the transformation in general will not satisfy all of those constraints. So this is an overdetermined equation system. And in general, you will not solve, they will not agree with each other. So you can think of this as in the following problem. So let's say I'll do it into the 2 dimensions because it is easier to draw. But here we are in 9 dimensions. I cannot draw in 9 dimensions, so let's draw it in 2. So you have an equation system that specifies x1 and x2, and you have 2 equations. So one pair is giving you this equation, the other pair is giving you this equation, and this is the unique solution. What if I give you another pair? If I give you another pair, and it is consistent with all the other pairs, then we go exactly through the same solution. But what if this is not the case? You have so you have the same situation as before, but now the third pair is like this. Okay, so what is now the solution? I have three equations, two unknowns, and there is no single solution for all the equations at the same time. So something sensible, okay, I will give you this point. This point is not the solution to any one of those. So it is not it even doesn't lie in any one of the lines. So living in a line, so this point lives in this line. So living in a line means the equation is satisfied exactly. So I have an exact equality. If you are a little bit off, let's say that you are off by epsilon. So that means that, so let's say that you have an equation that says, I don't know, this one here. It says x1 is equal to x2 plus 3. I don't know. So if you are in the line, you are exactly there. So you give me x2 and x1 is exactly x2 plus 3. If you have a little error, then this little error is translated here. Okay. So it is not exactly, so let's say that x2 is 3. So you would have 3 times 3, and this should be 6, but actually it is not 6, it is 6.1. And then you have a small error, 0.1. Okay, so you cannot satisfy all the points at the same time, all the equations at the same time, but you will find one whose distance to each one of the equations is relatively small. Okay, so let's call this equation 1, this is equation 2, and this is equation 3. So what do you want? You want that these errors are as small as possible. Let me make them blue. So the sum of all the errors is as small as possible. There is a drawback here, that is that these epsilons may have sign. So these are positive epsilons, these are negative epsilons. And then the addition of all those could be just go to 0. So let's make them square. So we want to find what is the solution, x1, x2, that minimizes these errors. And that will be this point. That will be that point in the middle. So it is not exactly at any one of those equations, but more or less it satisfies all of them. And no wonder this is called the least squares solution. So you look for the x1, x2 that is called in the stack that minimize this thing. So it is the least square solution. Have you encountered the least square solution before of a problem? Yes? Okay, so this is the meaning of this least square solution. Okay, so how do we look for the least square solution of this problem of colors? Okay, so we will do a trick. I can rewrite these 4 equations at the same time into a single one. So I can construct the matrix. I can construct a matrix that is this one. And then we have A. And then we have again R, I, and I. So now I have my 4 pairs. And what this equation is saying is this vector times this matrix should be this vector. This second vector times this matrix should be the second vector. So here, the vectors are column-wise. And then, what are the sizes of these things? Okay, so let's see. So this is a matrix that has 4 columns and 3 rows. So it is a 3 times 4 matrix. This should be 3 times 3. And this is 3 times 4. So everything so far is consistent. Okay, so let us call this matrix Rj. Let us call this one Ri. And then our equation is that this matrix times this one should be this one. Okay, so I will not prove the following, but how do we find, I will give you the trick, the kind of the recipe, but we will not give a proof for that. That is more algebra. Okay, so how do I solve for this equation? How do I find the least square solution of this? So I could go kind of halfway, writing all these equations here. I would have 12 equations. Now my A would be as a column there. But there is a much simpler way. Okay, so let's look for the simpler way. Okay, so what would I like to do? I would like to do the following. I am tempted of doing this. I multiply by the inverse of Ri on the right, and then I'm done. I have it. Can I do that? If you multiply by the inverse of this Ri from the right, you're done. Is that true? No. Because this matrix is not a square and it doesn't have an inverse. Okay, so, but we want to do that, kind of that. So let's code it. Okay, so let's see if we can play a bit with this algebra. Okay, so I have this. And I can multiply on the right by Ri transpose. Ri transpose. Okay, so let's look at the sizes now. So these matrices were 3 times 4. Okay, so now the sizes are 3 times 4. This is 4 times 3. This is 3 times 3. This is 3 times 4. And this is 4 times 3. So now, all this thing here, all this thing is 3 times 3. And all this thing here is 3 times 3. And now, unless there is some very bad problem, this bad problem is called multicollinearity or collinearity. But unless there is a problem with the colors that I have chosen, this matrix, it will be invertible. So if it is invertible, I can multiply on the right by the inverse of that thing. Now that would be Rj Ri transpose, and then the inverse of that Ri transpose minus 1 equal A. And now I have solved for A. Now I have my solution. And let's compare this equation here with this equation here. So it has the same structure. So we have Rj, and then we have this thing that is the quoted inverse. Actually, that quoted inverse is called the pseudo inverse. Pseudo inverse. And sometimes it is denoted like Ri minus. Okay, so now we know how to find that matrix A. Okay, so let's look at the slides again. So everything that is explained here is what I have done in the whiteboard before. So we have a color I want to multiply it by a matrix, and then I should have a new color. And I have the pairs of this color should transform into this color. And then my unknowns are the matrix. And then this is A minus 1, but we will not use it. A minus 1. And then you have the pairs of colors that correspond to each other. This is the, yeah. So where is A minus 1 coming in? So if I want to go from, I have two images. I have image I, and I have image J. And I take a color here, and I want to transform it there. And I'm using for that the matrix A. If I want to go in the opposite direction, so you take a color from J and you want to have it in I, you have to use A minus 1. That exists because this is 3 times 3. So it depends on which direction you want to go. Yeah, you have to use A or A minus 1. And you have to specify clearly in which direction A is acting. So here it is clear that A acts on I colors. And it transforms I colors into J colors. Okay, so let's make a break. Okay, we are here. So this is the least squares formulation that we had before. So you had all the pairs. So you have color I1 should transform into color J1, color I2 into J2, I3 to J3, and so on. Doesn't matter if it is inverse or not. It only depends on which direction you're going. So now what we are saying. Tell us a joke.
In English or Polish?
In English.
Oh.
Polish we wouldn't understand.
We also don't understand Spanish.
Okay, so what's the biggest, the best thing of Switzerland? I don't know, but the flag is a big plus.
Alexander.
Doctor, my back hurts when I wake up in the morning. Don't wake up in the morning. No, wake up in the evening.
Okay. Okay, so this is this least squares formulation that we had before. La montaña chiterna.
Vamos a la corriera.
Venga.
Ahora que no te vuelvo.
Okay, so what this is saying is, okay, you will not manage to find a matrix that transforms exactly these 4 colors into the corresponding pairs. So you will not find a matrix, a single matrix that transforms this into this into this, and this into this, and this into this. So what you will find is something that approximately makes those transformations. So instead of maybe 17, 122, so instead of 17, 122, 114, you will find one that makes these, let's say, 110 instead of 114. And instead of 122, you will have 124, let's say. So what you are saying is so you will not find a single matrix that makes let me remember the numbers. This is what I want. But my transformation, this is a vector. My transformation will be such that it makes, I don't know, 19, 124, 110. And the difference vector between the two, the difference is this minus this is minus 2, minus 2. So, because we are not dealing now with numbers, we are dealing with vectors. Now, I will have an error that is not a single number, it is a vector. Yeah. And now I have to substitute these by, or to reduce this vector to a number. So what is a sensible transformation? So instead of having this minimization of this error, a sensible transformation is if now your error is a vector. You compute the norm and you square it. Actually, the norm, this norm here is epsilon that I plotted above. Okay. So what you want to have is that the transformations for each one of the pairs. So let's say that we have k pairs. So what you want to have is to minimize the sum over all k of what do you want to achieve? I want to achieve Rj minus Ri. This is the kth pair, so this is the pairs were before weight. So I'm using the same color for weight. Then square. And this minimization is done with respect to what? So let's put some numbers so that we don't get lost. So this goes from 1 to 4 because I have 4 pairs. Okay, so this is the minimization with respect to what I'm looking for. I'm looking for the matrix. So this is a minimization with respect to A. And it will give me the best A. Okay. The best is normally denoted with a star. And then we recognize here again the same problem that we have. So this is the least squares problem. And these differences, this norm here, this norm, not the square, but this norm is the epsilon. It is the distance between the point that you find, that is this one, this is the point that you find, and the point that you want it. Okay. So, yeah, so this is the formulation of this problem. This is the formulation of this problem. And I would like to have something like the inverse. Yeah, the inverse of A exists. So I want both these are colors in J because now we are going A minus 1 goes in the opposite direction. So these are colors in J, and I want them to be similar to colors in I. And now you know where this solution is coming from. This solution we have already derived in the whiteboard. Okay, so then, yeah, this is MATLAB code for that. Let's look at this. Okay, so let's say that we have this problem of H image, and we want to find correspondences. We already know the correspondences. And then we find the A. Okay, so let's do it with 3 colors only. Let's do it with only 3. So we were given 4 pairs. We were given 4 pairs, but we take the first 3, let's say, and now we would know how to solve it without the least squares, because we have 9 equations, 9 unknowns, and I can compute it. So I could exactly find the A in that case, and there is only one A. Okay, that is what you get. So the degraded image would go into that one. Okay, it is better, but not quite what we wanted. So now, if we use the least square solution, so you see that those are similar, but not exactly. So another correction using 3 other points. Now, again, depends on which 3 you are taking. You have one output or another. So now we use all the mappings, all the 4 pairs that we have. And now it is much more the result. It looks much more like the result. And this is MATLAB for that. Okay, any question about this? So what is the equivalent of this having taking the 4 pairings or just 3? Okay, so let's again in okay, so let's do it 2D again, because this is something we can do easily. So we have x1, we have x2, and then we have our 2 lines. We are given 3 pairs, let's say, instead of 4, because now we are in 2 dimensions only. And then this would be taking, for instance, you take 2, you have more equations than unknowns. This is what we have when we have 4 pairs instead of 3. So we take 2, any 2. So I will take this one and this one. And then this is the solution. If you take another pair, that is this one and this one, then this would be the solution. And if you take the other pair, this would be the solution. So depending on which pair you take, you have an exact solution, but it is not the solution that you want. The solution that you want would use all the information that you have around, and it would be much better. This is the equivalent of this problem in which we are given 4 pairs, so we are given more equations than unknown, and then I take 3 of the pairs, because with 3 pairs I can find exactly one solution, so we are exactly at one of the crossings. But depending on which pairs I take, I have one solution. For instance, this one here, I have this one here, or I have this one there. So those are 2 different points in this 9-dimensional space. And then if I use the 4 of them, then I have something that is more or less in the middle, and that corresponds more to what I want. Any question about this? No question. Okay, so now let's move on to the next topic. The next topic is the Fourier transform. So let's remind a bit what the Fourier transform is. So the Fourier transform tells you that you can take, we have multiple Fourier things around. So we have Fourier series, Fourier transform, and both for discrete and continuous signals. So let's clarify a bit on this soup of Fourier things. So we have 2 things. So we have Fourier series. Fourier series, we have Fourier transform. And then we have discrete signals, and then we have continuous signals. I should have organized this differently. Continuous signal. Okay, so this is a reminder. Let me put it in this way. So we have a Fourier series and then Fourier transform. Okay, so let's start with what is the difference between Fourier series and Fourier transform? You may remember signals and systems.
One is for periodic signals.
For?
Periodic.
Yeah. So the difference is periodicity of what you are transforming. Okay, so let's say that, yeah, so let's make some drawings. So here we would have time, we would have here x of t, and then we have something that is periodic. So it goes like this. Then the Fourier transform, let's make Fourier transform of this. Fourier transform now, it has an axis omega. This is called x j omega. And this is a complex number, so we only plot the amplitude because we cannot plot complex numbers as such. And then it would look something like this. Okay, then we have for discrete signals. So the equivalent for discrete signals is this thing. So we have this axis. Now it is called n. This is x of n. And now we have this kind of signals that are periodic. And another Fourier transform. So the Fourier transform, I'm running out of space. Let me erase this. I will put the Fourier transform below. So Fourier transform is something that is periodic. So that's 2 pi. I will draw only one side, the other side is equal. So it is something like this. Let's say here it is pi. And then we will have this. J omega. And this is the axis of omega. Okay. And on the other side it is periodic. So it has periodicity 2 pi. Okay, so that is for periodic signals. Okay. Yeah, actually, I made it wrong. This is the Fourier transform. I'm mixing here. So let me fix it. We have Fourier transform. Fourier transform is similar. Actually, it looks very much like this one, but now we don't have anything periodic. So this would be x of n. And the Fourier transform looks similar again. So the Fourier transform looks like this. So this is x of a j omega. Okay, so then what is the difference between the two? The difference is that this one is sampled. So this one comes from sampling this one at given frequencies. And the number of frequencies is related to the periodicity. I don't want to enter into that. How many samples you have here, depending on the sampling, on the number of the period of this signal and so on. I don't want to explain that. So this one here is called xk. So xk is the Fourier series, while this one, that is the sampling that is coming from, it is the Fourier transform. So the Fourier series is just taking the Fourier transform and sampling it at given frequencies. The same here. So if you have a single signal, single pulse, and it goes to zero all the time, then the Fourier transform is that one. So the Fourier transform is this one. This is x plus omega. And then the difference is that one is sampled. So let me write. So this one is a sample version of this one at given points. And again, I don't want to enter into how many samples you need and so on. So this one here is the Fourier series. This one there is the Fourier transform. And this is also called XA. So here in this kind of zoo of continuous discrete signal Fourier series, Fourier transform, the difference is whether the signal is periodic or not, and whether the signal is discrete or not. Okay, so let's go further. Okay, so what is the Fourier transform tell you? Okay, so the Fourier transform of the Fourier series, let's do it with the Fourier series that is a bit simpler to visualize. Let's say that you have a signal that is like this. Okay, so this is my signal. I will put the signal now in green to distinguish it. So the signal will be in green. It is periodic. Okay, so this is time. This is x of t. So the Fourier transform tells you can decompose any signal. There is again subtle details about discontinuities and so on, but let's forget about those. Then this one can be decomposed into a sum of sinusoids. So this sinusoid is something like this. And then, so it goes through the same zeros as this one, and it has more or less the same amplitude. So you have to control what is the periodicity of this sinusoid. This is called the wavelength. This is represented by lambda. And lambda is 1 over the period. So except the time separation of 1 over the frequency. So it is also called period. And this 1 over the frequency. It's called the frequency omega. C. That is the fundamental frequency. So it is just the inverse. This omega c is just the inverse of the wavelength. And so you have to control the wavelength. So there are two ways. So there is something that you have to control. That is the wavelength. What else? I have to control the amplitude. So I have to control what is the amplitude of that. What is this height? So So that is also something that we have to control. And then I have to control whether I shift my sinusoid to the left or to the right. So I have to decide what is the phase of the sinusoid. So that is something also that I have to control. So for a given sinusoid, this sinusoid here, I have to say, okay, you will decompose x of t will be for the first frequency, for the fundamental frequency, it will be A naught, and then sine of 2 omega naught t plus phi naught. So those are the three ingredients that we are controlling. What is the height, is the frequency, or in other words, what is the wavelength, and what is the phase. So this one is controlling the sinusoid in this direction, how wide it is. This one is controlling it in this direction, where to place it. And this other one is also in this direction, that is how wide it is. That is for the first one. And it turns out that the second one, so the second sinusoid that I'm running out of colors, and that's maybe this one, let's say. So the second, let's make it. Do I have more colors? Can you choose the colors? This is so nice. Okay, now the second one. The second one will be an harmonic of this one. I'm very bad at drawing, but we have to fit. Here we have a single period, so I have to fit 2 periods there. And let me see if I'm able to do that. Okay, so let's make it 1, 2, and I come back here. Okay, and the same on the other side. 1, 2, and then I come back. So now this period here, this is the period of the new one. This is the period of the new one. So now this would be T naught, or T naught, and I know. And the new one, that would be T1 lambda 1, that is 1 over omega 1. It turns out that omega 1 is twice omega 2. So it turns out that this is, twice omega naught. So I have to control for the new one plus A1 sine. I don't have to worry anymore about the frequencies, because all the frequencies, they turn out to be on multiple of each other of the first frequency, and then find one. So I have to choose A1 and phi 1. The frequency I don't have to choose. And actually, this frequency here I don't have to choose it either, because it is related to the frequency, to the periodicity of x of t. So you only have to keep track of 2 numbers. You have to keep track, so this one here, we don't have to keep track of it, because it is given by the periodicity. You have to keep track of the amplitude and phase of each one of the harmonics. And then you would keep adding. So you have to add many more terms. So what they are saying is that for periodic signals, this periodic signal is equal to the sum of all harmonics. So you need, actually, for a continuous signal, you need infinite harmonics of AK cosine of K omega 0 plus phi. and this k goes from 1 to infinity, we are missing one term that I made this signal to have zero height, but we may add it. Okay, so and then we would have something like so this one here plus some constant that shifts everything. Okay, so and we have to keep track of these numbers. Okay, so there is an alternative way of expressing that. That is, okay, so let's use complex numbers. And now, the Fourier series can be written in this way. It goes from minus infinity to infinity, ak, and then a to j by k. And then, instead of having this cosine, what I have is this. There is a t missing. And then a j k. But now k goes from minus infinity to infinity. There is another way of expressing. These 8k and 5k, they are not exactly the same as these ones. They are different. Okay, so let's call them prime. I abuse of the notation, just to not make it too clumsy. Okay, and even this term now is included. When k is equal to 0, this is a constant, and then I can put whatever value I want there. So now we see why. So those are the numbers that I have to keep track. And that now we understand why the Fourier transform or the Fourier series are complex numbers. So they can be expressed as a sum of sinusoids, and this is what is shown here. So if you want to reproduce the signal here, you need to add a lot of signs. And you need to add a sign with this height, a sign with this height, a sign with this height. Actually, we are not very good in this, but all these frequencies are multiple of each other. Okay, so this is the fundamental frequency. And then the second one, you see that it has 2 cycles, as I wanted to do. So it has 2 cycles, 1, 2, where the other one has only 1 period. And then, or half a period. And then you would have all the harmonics. So all these frequencies are multiples of the fundamental frequency. And you recognize here, you recognize all the ingredients that we have. So let me copy it. What do we have? So we have the square t, which is x of t, is equal to the sum. So probably it means here from 1 to infinity. Well, 2 pi over lambda plus 1. Like that. So we see all the ingredients here. So this is the sum, lambda 1 plus 1. So this is the amplitude. And then the sine of what? This is omega 0. So this is omega 0 to nc plus omega 0 yeah, actually, we don't need to rewrite it any other way. I wanted to extract the phase, but we don't have the phase. So, what are the this is the amplitude. This is the of the n harmonic. This is the frequency. This is 2n plus 1 omega 0. So meaning we only have odd harmonics. We only have odd harmonics, all the ones in which, so all the harmonics for which n is not so good. All the k for which k is a multiple of 2, they are 0. That is why we write it this way. And then 5k, all of them are equal 0. That is why they don't appear. So, you need to keep track of two things. The amplitude, the phase. In this case, the phase, all of the phases are 0, but we have to keep track of them. And then add a lot of signs. And this is for periodic signals. Okay, good. Then, so these sinusoids, they are called basis functions. And whatever goes in front, they are called the Fourier coefficients. So here, these are called basis functions. And these are called Fourier coefficients. Okay. What else? Okay, so those are the basis functions, Fourier coefficients. And you see here how if you keep adding more and more terms, you get closer and closer to the wave you want to reproduce. So if you add just one sign, this is this square pulse. And then if you add just one harmonic, okay, it more or less has the same periodicity, but it doesn't look like something square. And then if you add 2, it's a little bit more similar. 3, or no, 2, 4, 8, 16, 32 signs. There is this overshooting caused by the discontinuity, but aside from the discontinuities that are not well represented by Fourier, all the rest, it looks very much like the square signal that you wanted. And yeah, so those are the ingredients that you have to control. So you have to control the amplitude, you have to control the periodicity and the phase. And in general, you can write in this way. Okay, and we know now how to transform that into complex coefficients. Okay, so let's make it a bit more formal. Okay, so how do I compute all these numbers? Because they look like magic, right? So how do you get these amplitudes, these phases? So for doing that, let us think of how you represent vectors, standard vectors. Okay. So let's say that you are in two-dimensional space. You are in a two-dimensional space, so you have x1, x2, and you have a vector here. So you have a vector here that is the point x1, x2. Sorry, x1. This is that point, and this gives you a vector that is x1, x2. Okay, so what is this? This is x1 times this vector, 1, 0, plus x2 times this vector, 0, 1. And we will call this vector, we will call this vector E1, we will call this vector E2. So E1 is the unit vector in this direction, and E2 is the unit vector in this direction. And okay, so let's say that now I want to construct a new basis that goes like this. So this would be U1 and U2. So how do I get now Y? So to get to R, I would have to go this length. Okay. What is the length of that? The length of that is I don't know, is the square root of x1 squared plus x2 squared. I have to go in that direction times u1 plus 0 u2. Clearly? So now my new coordinates in the u1, u2 coordinate basis, my new coordinates are these ones. So now my Fourier coefficients have changed. So my Fourier coefficients is what are the numbers that are multiplying by my basis part, my basis vectors. So now my coefficients have changed. Okay, so how do I, in general, how do you find these coefficients? Because this case was very easy, but how do you find those coefficients in general? And there is a trick. There is a trick that is, okay, so in general, let's say that you have R, and you have arbitrary basis U1, U2, so you have to find R. Okay, so it is R U1 times plus R U2 U2. There are a few assumptions there. Okay? And let us write the assumptions. The assumptions are that U1 is orthogonal to U2. And the other assumption is that the length of both vectors is 1. We have unitary vectors. And then in that case, this is true. Okay, so what is this? This is the dot product. So you have to define the dot product between two vectors. And then you define the dot product between two vectors, like for instance, let's say that you have the dot product between x1, y1. I'm running out of indexes. Okay, I don't know. Okay, so this is x1, x2 of the point 1, and then x1, x2. Let me not fiddle with numbers. Let's say x1, x2 of the point A with x1, x2 of the vector B. So you have vector A, vector B, you have the x1, x2 components. And then the dot product is this one. This x1a, x1b plus x2a, x2b. So this is the usual way we define the dot product, right? So once you have defined the dot product, once you have a dot product, you can automatically determine what are the coordinates of a vector in any arbitrary basis. As long as your basis is orthogonal, and unitary. What if it is not unitary? Okay, if it is not unitary, it is not too different. Only that I have to divide by I have to make them unitary. Okay, so it would be R U1. Now I divide by U1 squared. And which are these norms? Okay, so the norm of a vector, any vector, is UI, So it is the dot product between those two vectors. Okay, so let's recapitulate a bit. So I had a vector, this vector here. And we are used to think of it as x1, x2. But actually, x1, x2 is just this expansion. Only that we never write e1, e2, that are the unitary vectors aligned with the axis. We never write them, but they are there. If I want to express them in any other basis, I can do it very easily. It is this one. Now, the only condition for this to hold, so for this to hold, let me make it green. This is true if U1 is orthogonal to U2. So all we require is orthogonality. We don't require to be unit vectors anymore. And then what is the key? The key is to define an inner product. So given two vectors, how do you compute the inner product between the two? Okay, so this is just a reminder of how we express vectors in two dimensions, or in n dimensions. I'm afraid we are almost run out of time, but we have a bit more. Okay, so what has this to do with signals? I want to have the Fourier transform of my signal. So what does these vectors have to do? Because signals are vectors in some vector space. So they are vectors. And then this has the same shape as my expansion here. You see, it is the sum of some number. This is a number. All this is a number, and this is a vector. So it is a number times a vector, a number times a vector. This is what I have here. I have a number times a vector, a number times a vector, and I have to add many of them. So this is a change of basis only. So what are my Fourier coefficients? My Fourier coefficients, I have to, so if now in general I say, okay, this will be coefficient at scale. Okay, so this will be the sum overall, okay, of some coefficient ck, okay, ck times this vector. These are my unitary vectors. These are my coefficients. What are my coefficients? My coefficients will be the inner product of your signal x1 times this thing. So we divide this by will be that. And it is exactly the same that we were doing with vectors. I mean, 2 dimensions, okay, it is a little bit cumbersome, but we understand it. With Fourier transforms, it is not so easy. And we have not defined yet this inner product. How do you compute an inner product between a function, between 2 functions? So we have to define the inner product. So we have to define the inner product between any 2 functions. These signals are periodic. So they are periodic with figure t. So I will go from minus t hat to t hat of f of t multiplied by s. And that's it. So this is the complex conjugate. So you take f of t, multiply by the complex conjugate of your basis, multiply the 2, add, compute this integral, that is the inner product. And the same for this norm. This norm is also computed in that way. So what we are doing with the Fourier transform is exactly the same as we were doing here with vectors. Exactly the same. So the Fourier transform is nothing more, or the Fourier series is nothing more than expressing our signal in a different basis. I think that is enough for today. So tomorrow we will continue with all these ideas. Questions about this?
Can you move to the right, please?
The star is complex conjugate. You know the complex conjugate of a number? Yeah. Okay, so let's stop here.